Imagine a single musical note, say A4. At first, it feels almost empty. It's mathematically very perfect, but emotionally it's plain. Now imagine adding harmonics to it. Shape the attack, give it a rhythm. Suddenly, that sterile tone begins to feel musical. That transformation is the heart of today's episode. Welcome to today's episode. Music is not only an art form, it's also physics. What we experience as an emotion is also an organized science. In this episode, I will explain how music is generated, how audio analysis helps us understand music, and how these ideas directly connect to musical theory. The goal is simple. By the end, we should be able to hear music not just as a sound, but as an interaction between physics, maths, and creativity. Music begins with a vibration. A guitar string vibrates when it's plucked. A violin vibrates when it's bowed. A drum membrane vibrates when it's stuck. In flute, the vibrating system is the column of air. Take an electronic music. An oscillator creates a vibration that are later converted into sound by a speaker. When an object vibrates, it disturbs the surrounding air. It kind of creates alternative regions of compression and rarefaction. So these pressure variants travel through the air as sound waves and reaches. So before a music that you hear as a file, it's a waveform and it moves pressure in a physical medium. So the most important property that governs all this is frequency. Frequency is the number of vibrations per cycle. It's measured in hertz. In music, frequency is perceived as pitch. Frequency is widely used in many physical applications. Take a structure. A structure has a frequency. It naturally vibrates at natural frequencies. In a similar way, a music instrument vibrates. A low frequency gives a low pitch. A high frequency gives a high pitch. For example, the note A4 is commonly tuned to 440 Hz. If we double that frequency to 880 Hz, we say A5, the same pitch class but one octave higher. The physics says frequency doubling, but the music says is at octave. But real music instruments rarely produce a single frequency like what we discussed. A real note contains a fundamental frequency and then additional frequency. This additional frequencies are called overtones or partials. So when these partials occur in the integer multiples of the fundamental, we call them harmonics. So if we say that the fundamental frequency is 440 Hz, the harmonics may appear at 880 Hz, 1320 Hz, 1760 Hz, and so on. It's a multiple of the fundamental frequency. The fundamental frequency gives the note its pitch identity. The harmonic structure gives the note its timbre. So now you may be wondering what is a timbre. Timbre is the say a color of a tone. The reason a flute sounds as a flute and a violin sounds as a violin, though it plays the same note, but the sound is different. It's because of timbre. It depends on the harmonic content, spectral envelope, resonance, attack, and decay. It's one of the most important link between audio analysis and music theory. Pitch comes mainly from frequency, while timbre comes mainly from the distribution of energy across these frequencies and time. So now we have understood how basic music is analyzed, which can be analyzed. To analyze music using computers, we need to first convert this continuous sound into digital form. We can do this with the help of a microphone. A mic converts this air pressure into variations of voltage. Then an analog to digital converter transforms this continuous voltage into sequence of numbers. This number is what is coded in computer. This process has two main steps. One is called sampling and the other one is called quantization. So sampling means measuring the signal at regular intervals. The sampling tells us how many measurements are taken per second. Say a CD quality audio uses 44 kilohertz, which means it has 44,100 samples per second. So here we use a rule called Nyquist-Shannon sampling theorem. So to represent a signal accurately, the sampling rate must be twice the highest frequency we want to capture. Since humans can roughly hear up to 20 kilohertz, a sampling rate above 40 kilohertz is needed for the full audio range. If the sampling rate is too low, aliasing occurs. So what is aliasing? So aliasing is when frequency content folds back and appears as a false lower frequency. So in simple terms, it's an illusion. The computer hears the frequency, but that is not really, heard in that form because the frequency that it's been tuned to is very low. So quantization is the second step. It converts continuous amplitude values into discrete numerical levels. So bit depth comes here. So it controls how the amplitude levels are available. Say a 16-bit audio has 65,536 possible levels, while a 24-bit audio gives far more precision and range. So once we do this sampling and quantization, music becomes a discrete time signal. Each sample is just a number, but together these numbers contain, pitch or rhythm or loudness or timbre or harmony. So all this texture comes into this music after we have, once we after we have sampled and quantized, and when we put all of this together, we get a rich production texture. So now the music has become a digital signal. The next question is, what kind of analysis we can do on the digital music? What can we extract from it? So there are two perceptions in this. The first is the time domain. So in time domain, we look at the amplitude as it changes over time. This helps us understand what is the loudness, where it is silent, in which note it is attacking, and where the rhythmic events occur. However, music is deeply connected to frequency. Pitch or harmony or chords or timbre. This all depends on the frequency content. So to study this, we use the Fourier transform. So the Fourier transform decomposes a complex signal into its sinusoidal frequency components. So basically in time domain, instead of asking what is the amplitude right now at this particular time, it asks how much of how much of each frequency exists in this sound. So this is very powerful in music because music is built with frequency relationships. The fundamental frequency refers to the pitch. Harmonics relate to the timbre. No, low frequency gives us the warmth or the bass, whereas the high frequency, gives us the brightness or sharpness and air. So from this frequency spectrum, we can compute several useful descriptions. One is the spectral centroid. So this gives us the estimate of the brightness. And the other one is the spectral bandwidth. This tells us how the spec spectrum is spread across. The next one is spectral roll-off. This tells us the frequency below which most of the energy lies. And the last one is spectral flux. This measures how the spectrum changes from one moment to the next, which is useful for detecting the onset and the transitions. So the four descriptors are: first one is spectral centroid, second one is spectral bandwidth, third one is spectral roll off, and the fourth one is spectral flux. When we do a normal Fourier transform, there is one major limitation: it loses the time information. If we analyze the entire song at once, we may know which frequencies occur, but we do not know when they occur. Music is non-stationary. Notes begin and end, chords change, drums hit, singers glide in between. So there are a lot of fuss going on. So this is where short-term Fourier transform or STFT comes in. So this STFT divides the signal into short overlapping frames. No, it applies a window function and then computes a Fourier transform for each frame, and these frames overlap. When we stack all those spectra over time, we get what is known as a spectrogram. So think of spectrogram as a X-ray of music. Though the horizontal axis it shows the time and the vertical axis it shows the frequency. The color or the brightness of the spectrogram it shows the energy. So horizontal lines usually represent sustained harmonics, vertical represents sudden transients, say a drum hits. There are some regions which are like diffused and cloudy. Those indicate noise-like situation, like it's a symbol or distortion. So these kinds are represented as diffused cloudy region. So this is how a waveform is converted into a spectrogram. That is, from a time domain, we have converted it into a frequency domain, and we can analyze there. So there are some features used in music. No, when we need to analyze music, right? It is measured by certain features. One among them is RMS energy. RMS stands for root mean square. So it measures the power of a signal, and it's used in loudness related features. So high RMS means it's very loud and more energetic, while a low RMS means it's indicates a silence or softness. Second is the zero crossing rate. It's called ZCR. So it measures how much the waveform crosses the zero amplitude line. A noisy or high frequency sound often has high ZCR. A smooth tonal sound usually has a low ZCR. Uh, it is simple, but it gives a lot of clues about the texture of the song. We can easily identify a noise from a song. The third is the spectral centroid. It indicates the brightness, and we have already discussed about the spectral bandwidth. It describes the spread, and spectral role of it describes how this energy is distributed across the spectrum. And the spectral flux, it captures the spectral change when the onset is happening, and so on. So these are all some spectral features which we combine everything, and I'm saying it as a third feature. The fourth and a very important one is the MFCC. MFCC is called Mel frequency sepstral coefficient. No, MFCCs are compact features that describe how the spectral envelope of sound is perceptually motivated using a frequency scaling. Say, it basically what it does is it approximates human hearing. We perceive low frequency differences more precisely than high frequency differences, same way the MFCC does. The pipeline for that is first is that we frame the audio. We saw how the audio is to be framed before, and then we compute the STFT that we discussed before, short term Fourier transform. We compute the short term Fourier transform, and then we calculate the power spectrum, and then we apply the filter bands, and then take the algorithm and apply discrete cosine transform. So MFCCs are very useful for instrument recognition or genre classification, or when we want to compare whether two similar audios. MFCCs play a big role there. And finally, the most important when it comes to music is chroma feature. Chroma feature map audio energy into 12 pitch classes. It's specifically designed in a way designed for music. C, C sharp, D, D sharp, E, F, F sharp, G, G sharp, A sharp, B. These are the um, notes we have. So it divides it into 12 pitch classes. And the powerful idea here is octave folding. So A3, A4, A5 different octaves all belong to the same pitch class A. Because of this, the chroma is extremely useful for chord recognition or harmony analysis or key detection or music similarity. It is specifically designed for music. In simple terms, MFCCs are strong for timbre, chroma is strong for harmony. Spectral features, that is spectral coefficient, bandwidth, roll off, and flux. These describe the brightness and texture. RMS and ZCR describe the energy and waveform behavior. So together with all these features, computer interprets the musical audio in a structured way. So let's once again see what are the musical features uh, that is used to analyze music. First is the RMS energy. So the main use of RMS energy and the ZCR is that it describes the energy and waveform behavior, and we can get several insights from that. And the next is the spectral features that we discuss: centroid, bandwidth, roll off, and flux. It describes the brightness and texture of the music. Next two are MFCC, which is strong for timbre, and chroma, which is strong to detect harmony. So how all this musical features connects to music theory? So a frequency corresponds to a pitch. When frequency increases, pitch increases. When frequency doubles, we perceive it as octave. That's why a A4 fourth octave is at 440 hertz and a fifth octave is at 880 hertz. It sounds like a related versions of the same note. Harmonics and spectral envelope correspond to timbre. Music theory may describe it as, you know, a sound we hear can be described as a bright sound or a rich sound or a sharp sound or a metallic sound. So the similar way audio analysis describes the similar qualities as centroid, bandwidth, harmonic content and MFCCs. Amplitude and RMS energy corresponds to the loudness and dynamics. In music theory, we speak about soft and loud passages, crescendos and decrescendos. In signal processing, we measure these changes using amplitude envelope and energy features. Time domain events corresponds to rhythm and articulation, note attacks, drum hits, rhythmic accents. So these appear as a change in energy and spectral flux. Beat tracking and onset detection. No, these are the computational features of listening to a rhythmic structure. This can be analyzed using time domain. When we take chroma features, these features correspond to pitch classes or chords and harmony. Say a C chord contains C, E, G notes. A chromogram can show the energy in those pitch classes, helping helping to estimate the chord progression in a systematic way and a harmonic movement. Next, melody. So melody corresponds to a sequence of pitch over time. Harmony corresponds to simultaneous pitch relationship. Rhythm corresponds to structured timing. Timbre corresponds to spectral identity. Audio analysis maps each of these features to the corresponding music idea. So, music theory and signal processing are not separate languages. They describe the same phenomena at different levels. So, music theory gives us the artistic grammar, whereas the mathematical microscope is given by the audio analysis. So, what it starts as a vibration becomes a pressure wave, the pressure wave become a digital sample and become a waveform, and the waveform become a spectra and spectrogram. Spectra becomes a feature using MFCCs and chromas, and features connect directly to pitch or timbre or rhythm or melody or harmony as we discussed. So the next time you listen to a song, imagine the hidden structure behind it, the harmonics, the spectrogram, the chroma patterns, and its representation. A song may feel emotional on the surface, but underneath there is also an elegant evolving time frequency architecture. That's it for this episode. Thank you.